Welcome back to our course on fluid flows for chemical engineers. In Module 1, we focused on the fundamentals of fluid mechanics, properties of fluids, pressure in static systems, the basics of dynamics, laminar and turbulent flow, flow in pipes, and the behavior of Newtonian and non-Newtonian fluids. Those concepts are the groundwork, but chemical engineers rarely stop at theory. We must take those principles and apply them to real engineering systems. In this module, we shift from the fundamental theory to the applications of fluid flow. We will explore how chemical engineers harness these principles in practice, in pumps and compressors, in fluid transport networks, in mixing and agitation, in fluidization, in multiphase flows, and in emerging fields such as computational fluid dynamics, CFD. Along the way, we'll also discuss practical challenges, pressure drops, energy efficiency, and scaling from laboratory experiments to industrial scale systems. By the end of this module, you will see how the theoretical ideas we studied earlier directly shape the design and operation of chemical plants, refineries, food processing units, pharmaceutical factories, and even renewable energy systems. Section 1, Pumps, Compressors, and Fluid Transport. Let's begin with the most basic and ubiquitous application of fluid mechanics, moving fluids. No matter the industry, if you are working with fluids, you need equipment to transport them from one place to another. In chemical plants, this role is usually performed by pumps for liquids and compressors or blowers for gases. Pumps work by adding energy to liquids to overcome resistance caused by friction, elevation changes, and pressure differences. There are different types of pumps. Centrifugal pumps, which use rotating impellers to increase fluid pressure and velocity, are the most common. Positive displacement pumps, such as piston or gear pumps, deliver a fixed volume of liquid per cycle and are used when precise flow control is needed. Compressors serve a similar role for gases. They increase the pressure of a gas so it can be transported or processed. Compressors are essential in petrochemical plants, refrigeration systems, and natural gas pipelines. When designing pump and compressor systems, engineers must consider the energy balance. Fluids lose energy to friction in pipes and fittings, so the equipment must supply enough power to maintain the required flow. Oversizing equipment wastes energy and money, while undersizing leads to operational failures. A common challenge in pump systems is cavitation, which occurs when local pressure in a liquid drops so low that vapor bubbles form and collapse violently. This can damage pumps and reduce efficiency. Chemical engineers must therefore design systems that maintain adequate pressure at all points. Section 2, Mixing and Agitation. In chemical engineering, fluids are rarely just transported, they are often mixed. Mixing may involve blending liquids, suspending solids, dispersing gases, or even promoting chemical reactions. This is where agitators, stirrers, and mixing tanks come into play. The effectiveness of mixing depends heavily on fluid flow patterns within the vessel. At low speeds, the flow may be laminar, leading to poor mixing. At higher speeds, turbulence develops, enhancing mixing but increasing energy cost. Engineers must strike a balance between mixing efficiency and energy consumption. Different impeller types create different flow patterns. For instance, radial flow impellers push fluid outward, creating strong turbulence but limited vertical mixing. Axial flow impellers drive fluid along the shaft axis, promoting circulation throughout the vessel. Anchor or helical impellers are designed for high viscosity fluids such as polymers, paints, and food products. Mixing is especially critical in industries like pharmaceuticals, where uniformity of drug formulations is essential, or in polymer manufacturing, where uneven mixing can compromise product quality. Section 3, Fluidization. One of the most fascinating applications of fluid flow in chemical engineering is fluidization. A fluidized bed occurs when a fluid is passed upward through a bed of solid particles at a velocity high enough to suspend them, making the mixture behave like a boiling fluid. Fluidized beds are widely used in catalytic cracking, coal combustion, drying, coating, and polymerization. For example, in petroleum refining, fluidized catalytic cracking units use fluidized beds of catalyst particles to break down heavy hydrocarbons into lighter, more valuable products like gasoline and diesel. The advantages of fluidized beds include excellent mixing, uniform temperature distribution, and high rates of heat and mass transfer. However, they also come with challenges, such as particle attrition, erosion of equipment, and the need to carefully control fluid velocities to avoid unwanted entrainment of solids. Understanding the fluid mechanics of fluidization, pressure drop, minimum fluidization velocity, and stability of fluidized states is essential for chemical engineers working in energy and petrochemical industries. Section 4. Multiphase flow. In real chemical engineering systems, we often deal not with a single fluid, but with multiple phases interacting, gas-liquid, liquid-solid, gas-solid, or even gas-liquid-solid. This is known as multiphase flow, and it is one of the most challenging topics in fluid mechanics. Some common examples include gas-liquid flows in distillation columns and absorption towers. Liquid-solid flows in slurry pipelines and crystallizers. Gas-solid flows in pneumatic conveying systems. Gas-liquid-solid flows in fluidized catalytic reactors. Each type of multiphase flow exhibits different flow patterns, such as bubbly flow, slug flow, annular flow, or stratified flow in gas-liquid systems. Predicting these patterns is vital because they affect pressure drops, heat transfer, and reaction rates. For instance, in a gas-liquid reactor, the size and distribution of bubbles determine how efficiently gas dissolves into the liquid, which in turn controls reaction efficiency. Similarly, in slurry pipelines, engineers must balance flow velocity to prevent particle settling without causing excessive wear on the pipe walls. Multiphase flow is one of the most research-intensive areas of chemical engineering, as predicting and modeling these systems remains extremely complex. Section 5. Heat and mass transfer in fluid flows. Another major application of fluid flow is in heat exchangers, cooling towers, and separation processes, where fluids are used to transfer heat and mass. The efficiency of these operations depends on how well fluids move and mix. In heat exchangers, the flow arrangement, whether parallel flow, counterflow, or cross-flow, directly influences how effectively heat is transferred. Turbulent flow enhances heat transfer but increases pumping cost, while laminar flow may reduce cost but limit efficiency. Engineers must design systems that balance these trade-offs. Similarly, in processes like distillation and absorption, mass transfer between phases depends on fluid flow patterns. Good mixing and turbulence improve contact between phases, enhancing separation efficiency. Section 6. Flow measurement and control. In industrial practice, it is not enough to move fluids, we must also measure and control them. Flow meters, such as orifice plates, venturimeters, rotimeters, and modern digital sensors, allow engineers to measure flow rates accurately. These measurements feed into automated control systems that regulate pumps, valves, and compressors to maintain desired operating conditions. Control of fluid flow is essential in processes requiring precise ratios, such as blending chemicals, feeding reactants into reactors, or maintaining cooling rates in exothermic reactions. Without reliable flow control, product quality and plant safety could be compromised. Section 7. Computational Fluid Dynamics, CFD. Finally, let us consider a modern tool that is transforming fluid flow analysis, computational fluid dynamics, or CFD. CFD uses advanced numerical methods and high-powered computing to simulate fluid flow in complex systems. Instead of building expensive prototypes or running trial-and-error experiments, engineers can create virtual models and predict how fluids will behave under different conditions. Applications of CFD in chemical engineering include optimizing reactor design for better mixing and conversion, reducing pressure drops in piping networks, designing more efficient heat exchangers, studying multiphase flow patterns in distillation columns, reducing emissions by modeling combustion processes. While CFD does not replace experiments entirely, it has become an indispensable tool for saving time, reducing costs, and gaining insights into systems that are too complex to analyze analytically. Section 8. Safety and environmental considerations. Fluid flow systems are not just about efficiency, they are also about safety and sustainability. Leaks, ruptures, and uncontrolled flows can lead to accidents, fires, or environmental pollution. Engineers must therefore design systems with safety margins, pressure relief devices, and fail-safe controls. From an environmental perspective, optimizing fluid flow reduces energy consumption, lowers greenhouse gas emissions, and minimizes waste. For example, better pump design reduces electricity use, while improved flow in scrubbers and filters enhances pollutant capture. In today's world, where sustainability is a core engineering responsibility, fluid mechanics plays a central role. Conclusion of Module 2. In this second module, we have connected the theoretical foundations of fluid mechanics to their real-world applications in chemical engineering. We explored pumps, compressors, and fluid transport systems, emphasizing the need to balance energy efficiency with reliability. We looked at mixing and agitation, critical for blending and reaction processes. We examined fluidization and multi-phase flows, which form the backbone of many industrial operations. We also saw how fluid flow principles shape heat and mass transfer, flow measurement, and process control. Finally, we touched on computational fluid dynamics as a powerful modern tool and highlighted safety and environmental considerations. Together with Module 1, this completes a holistic overview of fluid flows for chemical engineers. You now have the conceptual and practical framework to analyze, design, and optimize fluid systems across industries ranging from petrochemicals to pharmaceuticals, energy, food processing, and beyond. Remember, fluids are everywhere in chemical engineering. Mastering their behavior is not just an academic exercise, it is the key to becoming an effective engineer capable of solving real-world problems.